This video is the third of a continuing series analysing historic Formula 1 cars using CFD. Last video analysed the McLaren MP4 from 1984. This video will be analysing the 1985 and 86 versions of this car, the MP4 2B and C. Adding to the one gained in 1984, it picked up a further 2 World Drivers' Championships with Alain Prost. Even though it was definitely not the best car in 1986. But the improvements made in 1985 were significant in the context of Formula 1 aerodynamics. Ignoring all the mechanical improvements, which there were many, we focus on 3 different features from the 1985 and one from the 1986 car. In 1985, the winglets were outlawed, changes were made to the rear wing end plates, diffuser, and a vertical deflector added inside the front wheel. The change from 1986 was the front windshield. Other changes that won't be addressed here were the changes to the mirror, and the radiator exits seem to be a little bit further back. There was a change to where the turbo inlet was located, but this seems to be more of a packaging rather than an aero thing. This experiment ran 4 simulations running 4 different model configurations. The changes included end plates, diffuser tabs, vertical deflectors, and windshield. Test 1, the end plate resorted back to a simpler but larger shape, extending all the way down to the diffuser exit and forwards closer to the axle. Test 2, the diffuser tabs added vertical sections at the edge near the rear wheels with a small horizontal section. This was the first time flow conditioning elements were run within the diffuser, clearly aimed at improving the rear wheel and diffuser interaction. Test 3, the last for the 1985 car, was the vertical deflectors inside the rear of the front tyre, essentially a priori form to the contemporary barge boards that were discontinued after 1985. McLaren wasn't the only team to run this deflector. I spotted it on the Lotus as well. To test 4, finally the windshield had significant amount of work put into it, as there are images of some interesting solutions trialled. It was seen from previous simulations that the rear wing was considerably impacted from upstream disturbances. McLaren was clearly aware of this, and this model reflects the solution they used throughout 1986. The mirrors were not modelled because they take a significant amount of effort, and they only make aerodynamicists sad. Now to the experiment. All the parameters are the same. Essentially, once a case has been set up in OpenFoam and works well, it is just a matter of rerunning with minor changes to the wheel speed and axle positions. All the parameters from now on will be added to the description. Outputs from the front wing, rear wing, body, and total summation of the forces will make up the table of results. The results. I'll start with one of the key takeaways. That is, the rear wing end plate change is not effective on its own. The lift-to-drag ratio doesn't change from 8.1, the same as the 1984 wing. For the body, the efficiency decreased from 2.4 to 2.2. Re-establishing the efficiency to 2.4 is with the diffuser tabs. Then only with this combination of end plate and diffuser tab does the overall downforce numbers improve on the first MP4 test. However, overall it is now less efficient because the wheels are producing 67 more lift. So by making the diffuser more effective for the end plate model by adding the diffuser tabs, there is a remarkable increase in downforce. To the total, 105 newtons of downforce and 53 newtons of drag were added. Alone, the body was responsible for 122 newtons of negative lift, with 9 newtons of drag, basically all the additional downforce. Summing up the total from the aerodynamic components came to an increase of 33 newtons of lift and 26 of drag. Missing from the total is 28 newtons from the wheels in both lift and drag. The vertical deflectors near the front wheels are essentially a priori to today's barge boards. Their addition appeared to be effective at helping the car produce downforce. Initially I thought this was going to affect the body, making the floor more effective, but instead it was the rear wing. Its efficiency increased from 2.81 to 2.9. For the 1986 MP4-2C, the deflectors weren't run and the windshield was cut down flush with the cockpit's bodywork. I was worried that I was wasting my time with this simulation run, but the results were surprising. Comparing it with the previous test, both the rear wing and the body produced more downforce with minimum drag. This is something I really like about aerodynamics, its complete disregard for aesthetics. The previous windshield would seem to push the airflow over the cockpit, which it does, and should thereby reduce the downwind disturbance. But it doesn't, and the rear wing's lifted drag efficiency increases from 2.7 to 2.84. To summarise these results, a plot is needed. These are all the cars tested with the lift and drag numbers, and the lift divided by 2000. Using 4 significant figures is probably wishful thinking, but here it is. Here you can see the 1984 MP4-2 produces the most amount of downforce due to the winglets on the rear wing. It is also clear that the increase between 1985 and 1986 was minimal. The MP4-2 had really reached the end of its aerodynamic development, though changing the aggressive diffuser angle was never seen. Seen previously, these images are of the surface pressure maps. Test 4 has the largest amount of downforce produced by the body. When those force results were outputted, I thought the change in the windshield was just going to produce a disappointing pool of high pressure above the cockpit mock-up, but these images show that it actually came from the floor. The next highest downforce value from the floor came from Test 2. Even though the changes in numbers aren't large, it is apparent which floor is more effective. There is one point to highlight here. The high intensity blue doesn't continue very far into the diffuser, suggesting flow separation. I want to put the pressure plots from under the floor here because the floor is the place that is seeing the most change and has questions about the flow structure. As a complement to the pressure maps, the size of the puddles of blue equates to the lower pressure dips. A clue to the lack of effectiveness of the diffuser is seen in the red plot 400mm off the centre line. There is a high peak following the low which corresponds to the discontinuity of the dark blue. Even when the diffuser tabs were added in Test 2, it added a second low dip after that peak. That high peak is a problem. The wall shear stress doesn't indicate a large difference. I mean, there isn't a large difference in downforce numbers either. 186 newtons or 7.8% difference between the Test 1 and Test 4. However, there is an increase of 18% on the floor. Obviously this didn't come from a structural change. For the airflow over the helmet, the windshield clearly acts as a windshield, because when cut down in Test 4 there is more air impacting the helmet and the roll hoop. Why there is more downforce because of this isn't clear. A hint maybe at the radiator exit, maybe. Mapping the pressure through space is illustrative to see the pressure fields interacting. As we have seen, there is pressure changes on the floor coming in part from the top of the body. The cause could come down to any number of these three things: pressure, mass flow rate, and flow structure. Each of these need checking. Mentioned previously, there appears discontinuity in the flow pressure regions in the diffuser. I paused the animation at the rear axle to highlight this and how it differs with model configuration. The lesser blue regions mean their air isn't accelerating as much. As a basic rule for diffusers, the air should continue to accelerate through the diffuser. It's its primary purpose. The Vorticity X movie is supposed to show the differences in the vortex flow structures. The problem is that there isn't much difference again. The expected difference from the Test 3 deflector doesn't change the amount of rotating air that enters the radiator. The vortex core is pulled outwards of the side pods instead of impacting it. However, there's still rotating air entering the side pods. The Kinetic Energy X movie has been important for identifying the turbulence. This is probably going to be the last time I use this tool, as it tends to be only useful for identifying the changes in efficiency of components. With downforce becoming more dominant and the wheels the most draggy component, understanding the aspect of drag is secondary. The reason it could be interesting here is to understand the effect the cockpit has on the rear of the car, predominantly with Test 4, the MP4-2C. It appears that there is less turbulence impacting the rear wing. From the previous similar results that increased the wing's efficiency, this is predictable, but it's still surprising that it came from the cockpit. For the last two runs, I pulled out the X velocities for the X-axis to contrast the pressure maps where the air is accelerating to create the high and low pressures. These maps show the resultant velocities from this acceleration, or its integral to be more correct. For an example, I paused twice, just inside the Coke bottle tapering and at the rear axle. From test 3, the air under the wing has more high velocity, reflecting the higher downforce number, though the difference is only 35 newtons. Also seen in this picture, halfway into the diffuser is the region that produced 98 newtons more downforce for test 4. It is difficult to see any difference in this case, but we are talking 3% for the rear wing, 10% for the floor, and overall less than 1%. In terms of principles, the low velocity blue region that follows the car is where you want the air from under the car to fill. The bigger this region is, the more air you can fill it with. There isn't a large amount of difference in flow structure around the car for these 4 experiments. I'm going to conclude by summing up what I found, and what was interesting while the 3D Q maps are on the screen. The downforce loss from not having the wingless was never recovered, and the floor became the greatest component for creating downforce, increasing the floor's total percentage from 32 of the MP4-2 with the winglets to 42 from the MP4-2C. The small change in the diffuser is the most interesting. It had a dramatic effect on the performance within the established flow structure. Lastly, what surprised me the most about the development of the MP4-2 was that they never seemed to change the apparently very aggressive angle of the diffuser. From the discontinuity of the blue puddles, it is likely that the air didn't continue to accelerate through the diffuser. As a result, it would have amounted to a blockage and a less efficient device. It is surprising mostly because it would be a very easy thing to test in the wind tunnel. Even without a wind tunnel, it would have been a matter of track testing a number of different angles over the number of years the car ran. This basic diffuser tab is just the beginning of Formula 1 teams focusing a large amount of resources in this part of the car, finding all sorts of creative ways to extract performance when developing this area.